are these podcasts. Now, for all of your podcast needs, you can go to YouTube, available 24/7. Okay, this website is also on our course website, and you can just go to YouTube and type in "Chemistry is Fun for You," and they'll come up. Just find the channel. Okay, so they're all up and ready and waiting for you. Help you to go to sleep at night. Calculating vapor pressure, Jessica. Boiling point and freezing point. Jessica, my question is, what's there to calculate? Isn't boiling point, freezing point, even vapor pressure, aren't those things all in tables? You just Google this stuff. What's there to calculate? Some factor is changing. What factor is changing? Not pressure. If I dump in a little bit of sugar or a lot more sugar into water, does that change these things even more? Does it even change them? Jose, what do you think? Does it change it? Yeah, otherwise there'd be no point for today, right? And I dump in more sugar, it changes these properties of water even more. That's what they call them colligative. Colligative, meaning you dump in more solute, it changes these properties even more. So these are called colligative properties: vapor pressure, boiling point, freezing point. And why is it important? Well, there's the good, the bad, and the ugly. And I guess this is the good when you dump salt on the road, right? It melts the ice. So that means the freezing point had to go, Kathleen, up or down? Had to go down. It has to be super cold for that ice to freeze. If you have salt or something dumped, lowers the freezing point, right? And it gets on your cars, it ends up rusting and stuff. Boiling, and we're going to talk about why in a little bit. Imagining a solvent's vapor pressure. Let me go to this little animation here. Okay. You have a beaker of water, and you can see the liquid region, right, and the vapor region. And it's not, what I would like to have seen is a cover on the beaker, so you can actually reach an equilibrium. If you're not going to reach an equilibrium here, that stuff's just going to leave, right, and it's all going to evaporate. They should have had it sealed, so then you actually do reach an equilibrium between the liquid and the vapor phase. And if you do have a vapor phase, that means you have to have a pressure, and technically they call it there's the V, the vapor pressure. You can look it up in tables. Okay. If you dump in some sugar, what do you think that's going to do to this vapor pressure? Go up? So with the animation, I'm going to scroll down and show you, but it's just going to be this big blob in here, floating around. And it's just going to, essentially, all it does is just block the water from getting out. So there'll be less of it in the vapor phase. So in that sense, the vapor pressure should go down. And that's what, I don't think the animation is that good, but you see these little green and the blue balls there on the right-hand side, and there's supposed to be less water actually getting into the vapor phase, so it lowers the vapor pressure. Okay. So, and it doesn't really matter what the object is that you're dissolving into the water. Oh, something that blocks is something that blocks. So, no matter what you dump in water, the vapor pressure is going to go down. That's what I'm trying to get at. Okay. How do we determine, look at this question. How do we determine the vapor pressure of pure solvents? Valerie, how do we do that? Or how did we do that? If it's pure. Looked in it's in what I think for this upcoming exam, a table, right? You look in a table, and it tells you the vapor pressure of these pure water and things. Look in a table. Once you dump something in water, the vapor pressure goes down. Now you got to calculate it, right? There's no table for that. Okay, so there's 3 colligative properties, right? These properties change with the amount of stuff you dump in the solvent, the amount of solute you dump in the solvent. The first one is vapor pressure. And Jose, we said the vapor pressure goes up or down? You said the vapor pressure is going to go down, right? Vapor pressure goes down. So you got to calculate it. There's the equation. There's the equation. So, Lewis, if we want to know what the new vapor pressure is of water after we dumped in so much sugar, we have to calculate it. So we go through some work. We'll figure out what this other stuff is, but we go through some work to get delta P. And then we subtract it from what? How do we get the new vapor pressure? Vapor pressure is supposed to get lowered. So delta P is the amount that it's lowered by. Subtract it from that table. You have to look up the vapor pressure of this pure solvent, right? Oh, that's what it is when it's pure. But we dumped something in there so that it actually went down. How much? Delta P. So you got to find the table, right? Calculate your delta P and subtract it from the number in the table. That's the new vapor pressure. And that's what you got to do. And we'll do some homework on it. Okay. But how do you get this delta P? Grace, I think we spent maybe 10 minutes on this last semester. You recognize this stuff? PA0 and an XB? What's the A's and the B's? Yeah, A or B, the solute or the solvent. A is it's the vapor pressure of it. The A is the solvent. So how about the little superscript 0? They are consistent. You haven't seen this enough to know this, I don't think, Sochi, but what does that superscript 0 mean? Not degrees. It means pure. So whenever you see a superscript 0, that means, hey, look me up in the table, because that's for a pure compound. So PA0 is the vapor pressure of pure water, or the vapor pressure of pure cyclohexane, whatever the solvent is. XB. Now, all these equations are going to have a concentration term in it. XB is one of those concentration terms, Crystal. And looks like in the handout we have 4 ways to get concentration. Which type of concentration term is XB? If you don't use it, you lose it. 10 minutes is all we had of this, I think, in Chem 1501. XB is mole fraction, right? If you're not sure what it is, it's in the equations, but just the moles of solute all over the total mole. So the moles of solute divided by the total moles, multiply it by the number you get from the table, from the pure vapor pressure, and you get delta P. So then you take this delta P, subtract it from the PA0 in the first place, and you got your new vapor pressure. So that's the game that you play with vapor pressure. Lowering. The boiling point. What do you think? The boiling point, you dump in some sugar in water, the boiling point is going to go, she's right, but why? Why? I think of the vapor pressure story. Because for this stuff to boil, it has to get into the vapor phase, but now you have this stuff blocking it. It's going to be even more difficult to get into the vapor phase. So, yeah, boiling point should go up. And that's how those guys solved the problem. That's why there was a picture of spaghetti. Because the guys in Denver and all those guys, they have different boiling points than us because they're at a higher elevation, so lower pressure. So how do you fix the problem? Heck, maybe salt or a little direction, right? If they have you dump something in there, well, yeah, that's going to make the boiling point. Okay. So the vapor pressure goes up. More difficult to get the stuff to boil. It goes up by an amount, delta T. So to get our new Jessica, the homework is going to say, what's the boiling point of water after we dump in some stuff? So we use this equation to get our delta T. Do we add or subtract it from the true boiling point, the pure boiling point? Like water's supposed to boil at what, 100 degrees Celsius? We calculate a delta T. Do we add it or subtract it to the 100? We add it. The boiling point goes up. Exactly. You have to add it. Okay. So there's our, oh, sorry, wrong one. Boiling point. You have to add it. And there's our equation. What do you think the B probably stands for, Kathleen? Delta TB equals KBCM. Yeah, B stands for boiling. Or I think in the technical jargon it might be ebulliostic. But boiling, I think it makes a lot more sense. To me, it sticks better. So boiling. So one of these is the concentration term, just like before. Because these DAISY are colligative properties, the more point's going to get even bigger. One of these terms, KB or CM, is the concentration term. Which one is it? The CM. Valerie, we've got all these different ways, 4 ways to get concentration. Which way is this? CM. I'll give you a hint. The hint is the little m. Molality. Moles of solute over kilograms of solvent. Okay? Molality. KB, Jose, this is something that we're going to look up in the table. Let's say we dump sugar in water. Do we look up the little k for sugar, or do we look it up for water? Which one? Again, go back, in my mind, I go back to the vapor pressure idea. Right? You dump in this solute. It doesn't matter what the solute is, it just serves as a wall, as a blocker. So you don't care about that solute that you dump. Because a blocker is a blocker. So KB, you probably look it up for the water, for the solvent. Yeah, that's how it always is. You're looking up these constants for the solvent. Okay? And make sure you look up the KB and not, you look down to the next equation, not KF, because that's something else. You find a little KB for water and plug it in. Multiply it times molality, you get your delta T, add it to the true boiling point, because the boiling point goes up. So that's the part you got to remember. If they ask for what's the new boiling point, oh yeah, I use the boiling point equation, but you have to remember, oh, I have to add it to the boiling point of the pure solvent. If you don't know what it is, they got to tell you, or you Google it. Okay. Freezing point. We mentioned this earlier, Lewis. The freezing point goes, dump something in water, the freezing point goes down. It's like that ice idea, right? The ice melts, the freezing point goes down by delta T. So now it may not be water, it could be any solvent, Grace. To get the new freezing point of a solution, we have to subtract it from the pure. Right? Subtract delta T. And here's our equation. Delta TF is KFCM. Sochi, what do we say? KF, you do what to get it? Yeah, look at it in the table. For the solute or the solvent? Or the solvent. Right. And CM, again, recognize it, molality. Moles of solute over kilograms of solvent. Questions, Crystal? Because I know it's coming up. And they say so many grams of this and so many grams of that, and that's what's the new boiling point. And you never heard of these compounds. How do you know which one's a solute, which one's a solvent? You've never even heard of it before. Yeah, they use the word aqueous. You know the solvent is water. What if, Rebecca, they didn't use the word aqueous? They use so many grams of this guy, so many grams of this guy, you dump them in, what's the new boiling point? How do you know which one's a solvent? There you go. The one with the most is always the solvent. That's how you do it. So you don't have to know what any of this stuff is. The one with the most is always the solvent. Okay. Overall, these colligative properties, Jessica, are called vapor pressure, lowering, boiling point, Kathleen, elevation, and freezing point, Daisy, depression. That's the technical jargon for all this stuff. Here's our first question. A solution was prepared by dissolving 1.2 of naphthalene, 25 grams of benzene. What is the freezing point of the solution? Okay. What is the freezing point of the solution? So, Valerie, what equation are we probably going to be using to figure this out? Yeah, we'll probably need it, but what's the overall equation? All right. Anybody help her? The freezing point one, that delta T with a little f equals KFCM. Okay, that's the equation. So the idea is we got to calculate delta TF. And then we do what with it, Jose? What do we do with this delta TF after we get it? Subtract it from the original. Now here they are, right? Look in the bottom table. They have these freezing points. Which one? It's like Jose's right, Louis. We're going to calculate delta T, and then we got to subtract. Which one are we supposed to be looking at? First one. Do you agree? How did he know that benzene is the solvent? He's right. It's got the most. Exactly. Here, Crystal. There's 25 grams of benzene there. Right? So we're going to, that's the idea, we're going to get delta TF. Then our answer is going to be what? 5.5 minus our delta TF. And we'll have it. That's the big game plan. So how are we going to get it? Grace, what would you do first to get that delta TF? Oh, she says get that molality. Okay, let's get that molality. Good idea. My CM, if you look at the equations, it's the moles of solute all over the kilograms of solvent, but let's not write the word solute. Instead, Sochi, let's put what? Moles of moles of moles of naphthalene, right? I wouldn't write naphthalene either. I'd write C10H8 because it'll make a lot more sense, I think. Moles of C10H8 all over kilograms of solvent, but instead of writing solvent, Crystal, let's write C6H6. It'll look so much better. Okay. So, Rebecca, which one do you want to get? Moles of C10H8 or kilograms of benzene? Moles. Okay, how are you going to do it? Yeah. And what's the technical jargon? Molar mass, exactly, C10H8. So we need 10 carbons and 8 hydrogens. 10 times 12 is 120. 8 hydrogens, that's 8. So it should be 128. Right? So we have 128 grams in a mole. I'm going to go figure that out right away. 1.258 divided by 128. Yeah, about 0.0098. That's what I got, too. So that 0.0098. Now the kilograms of benzene. Jessica? Yeah. Perfect. He remembers 1,000 on the bottom. That'd be 0.025. Okay. So now we're running out of space here. My delta TF is going to be Cm, which is 0.0098, all over on kilograms of solvent, 0.025, times my Kf. Oh, I should have done that first. Oh, that's okay. My Kf is going to... You see it? Yeah. Is it the 5.065 or the 6.9? Because it's naphthalene. It's the 5.065 because it's the solvent. Okay, I got about 1.99. After all that. Okay. I got about 1.99. So is that, Kathleen, is that the answer? Go through all that work to get our delta TF, we got about 2. Is that the answer? The 1 point? Yeah, we got to take the 5.55 minus the delta T. About, what, 3.51? So we get 3.51. Okay. So whether it's freezing point depression, freezing point elevation, vapor pressure lowering, pretty much the same thing again and again. Just recognize which one's a solute and which one's a solvent. And what was the trick to doing that? The one with the most is the solvent, right? So there's more practice here. Another one. There's another one there. There's another one there. I want to jump to the very last one. Okay? Because this one's different. This one, I think, is the most difficult homework question you're going to come across with this stuff, these colligative property problems. We have, let's start underlining stuff. We have a 0.0182 gram sample of an unknown substance. It was dissolved in 2.135 grams of benzene. The molality of this solution was 0.0698 m. What is the molecular mass of the unknown substance? Jose, we've got all these equations, right? Do any of them have molecular mass in them? No, it doesn't, right? So, I mean, looks like they're talking about freezing point depression or something, but none of them have molar mass in it. So, but they're asking for molar mass. So that's why I think this is such a hard question. I strongly suggest starting out with what they want you to know. Molar mass or molecular weight. Louis, what were the units all the time? Grams over. It's grams per. Oh, that is the unit. Grams of what over moles of what? Really, Grace? It's grams of. Yeah, the grams of the substance over the moles of the substance. So in this case, we're asked, so it would be the grams of the unknown divided by the moles of the unknown. They call it the sample, right? You see that? They call it the sample. So let's just call it grams of sample all over moles of sample. And what I want you to kind of see is it doesn't matter if it's density, molar mass, whatever, it's an equation. Molar mass is the grams of sample divided by the moles of sample. And you can get molar mass. In fact, we're halfway there. They gave us one of these already, Sochi. Which one did they give us? The grams of the sample. What's the number? 0.0182. They already gave us that part. They already gave it to us. We just have to figure out what the moles of sample are. Okay, Crystal. Question's kind of changed now. Well, we need to find the moles of the sample. We'll divide it into 0.0182, and then we're done. We'll have molar mass, grams per mole. How are we going to get the moles of the sample? Okay, she's talking about this guy. Yes. Well, they don't give us delta TF, though. Oh, no, they didn't, did they? They didn't give us delta TF. I mean, and another hint is F, moles of substance isn't even in there. So this isn't going to help us. In fact, we may not even need this. Oh, there it is. If you use the molality equation, right? Because don't we know what the little cm is? What's the little cm going to equal? Yeah, that's what, 0.0698. They told us what it was. Now, Grace, it's the moles of, now you can say solute, but I guess, again, it's better to write something else. Right? Moles of, to be consistent, moles of sample, right? Since we're calling our unknown a sample. So it would be moles of sample all over kilograms of, Rebecca, what would you say? Now, don't write solvent. Again, it doesn't help as much. Kilograms of benzene. Kilograms of benzene. Now, it's the exact same thing as the molar mass equation, right? We have Cm equals moles of sample over kilograms of benzene. You know two things, you solve for the third, right? We're after moles of sample. So that means somewhere they gave us Cm, somewhere they must have told us kilograms of benzene. Jessica, how are you going to figure it out? Where is it? It has to be there somewhere. The kilograms of benzene. We're going to solve for the moles of sample. Yeah, to give us the grams of it. In fact, I think, didn't we ask you that last time? She had to convert grams into kilograms. Move it over 3 places, 0.00213 kilograms. Okay, so what we really have is 0.0698 equals our moles all over 0.00213. Since everything's in the right units, I just left them out. Kathleen, how are you going to solve for the moles of sample there? She says multiply. You see, she's exactly right. See why? It's that whole diagonal idea there. You got to move the 0.02135 to the other side. Okay. 0.00698 times 0.35. I get about 1.49 times 10 negative 5. What did you get? Oh, let me write down what you got. Yeah, 1.49 what? 10 to the negative 4. Okay, now we can plug that number all the way back in up here, and we should get our molar mass. All right, 1.49 times 10 to the negative 4. And what did you get? Anybody get an answer? About 122? 22. Yeah. So, again, hard question, because we're used to getting into this mode, oh, we have to use one of these equations, right? This question, we didn't even use one of our equations. All we did is use the molality equation. Okay? But the reason why it falls into this section is that they do this all the time. For proteins, enzymes, these huge, there's no other way to get their molar mass. And it's pretty easy. Freezing point depression. Put it in water, see how much the freezing point goes down, and you can calculate really easily the molar mass. Okay? By doing exactly what we just did in that calculation. Okay. And it all started out by, they asked for molar mass. That's why we started out this way. What's molar mass? The grams of sample over the moles of sample. And then you just kind of pick away at it, and it'll come. Okay, let's go back up here. We have an aqueous solution of a molecular compound. It freezes at negative 0.086 degrees Celsius. What is the molality of the solution? Daisy, what are they after? The molality. Now, what's the little symbol for molality? Little m, but in all of our equations, we don't have little m. We have what, technically? Little cm is what we're after. Right. So we're really after little cm equals what? That's our big goal here. So, Valerie, how are we going to go about and get it? Any ideas? We'll start with a big equation. What big equation can guide us in all our work and our effort? What equation could we use? Yeah, the delta T. Yeah, the delta TF equals KFCM. Works great because CM's in that equation. All I got to do is 3 variables. They gave us 2 of them. Just got to figure it out. Figure out what they are. So we're going to solve for that CM. There it is. Jose? They had to have told us delta TF and KF. They had to. Just got to look at it and we'll figure it out. Which one do you see? That delta TF or the KF? Yeah, what is it? 1.86. All right? They gave us the KF. We're looking for that little CM. That means they had to give us the delta TF, Lewis. Had to give it to us. It's hard. I think it's hard to see because it's a trick question. The reason why it's a trick question is because it's water. Hint. Water freezes at what temperature? That's the. So whenever they tell you, whenever they tell you the new freezing point, that number is delta TF. It is delta T because it froze at 0 originally. So you got to subtract it from 0. Well, then you get the same number again, but you put a little minus sign on it. Right? So our delta T is really what? Well, not the 0 though, just the 0.086. Because you take that 0.086, like take 0 minus negative 0.086. So the delta T is really just the 0.086 part. Does that make sense? Not the negative. Because you take your delta T and subtract it from the original, the pure freezing point. So the delta T has to be 0.086. Is that clear? And that only works for water. Everything else, you're going to have to actually calculate it and figure it out. So this is just 0.086. All right? So we just need to do what, Grace, to get our answer? Yeah, divide them out. 0.086 divided by 0.086 divided by 1.86. I got about 0.046. In Sochi, I should probably put what units on that? Molar? Or what? What's the little symbol that I should put on this? For CM. What's the little symbol that they use for it? Now, CM is supposed to be not molarity, but molality. Molarity was big M. Molality is little m. Like the hint, I guess, is a little subscript there. Put a little m on it. See if you can knock this one out. If you get stuck, just ask. I'll be glad to help you out. Got a few minutes left. Man, this is a complicated question. Game plan? To to me, this question goes back a couple class periods. If we knew what, think of it this way, if we knew what molality was, and they told us that, oh, you have 100 grams of the solvent, right? Because molality is the moles over the solvent. If you multiply molality by the kilograms of solvent, you get moles. And then we just convert it to grams, and we have our answer. That's how we did those, right? They have, because look, they have 100 grams of water, right? That's really, is that the solvent? The water the solvent? Yeah, because something's dissolved in something else. So that's our solvent. And that's really 0.1 kilograms. If you move it over three places, H2O. Right? So really, if we know molality, right, that's going to be the moles of, I shouldn't write solute. I'm going to write NH2, right? Actually, what the solute is, kilograms. It goes back to that class period where we have, they're going to give us 2, we solve for the third. We're going to figure out what CM is by using our delta T equation, right? They told us the kilograms of water, so we just solve for moles of urea. Converted it into grams. You see that? Does that make sense? So first, get CM. Second, use CM to get the answer. Grams of urea. Bless you. You see how to do it? How do you get CM? Make sure you pick the right delta T equation. It's going to be the delta TF, the delta TB one. Delta TF, yeah, because we're talking about it where it freezes. So you have the negative 0.085, that's just your delta T, remember, because it's just water. So there you know delta T. They told you what KF was. You can find CM, and then use it to get the gram. Now all these solutions are posted online. Check them out, and I'll be glad to help you. If you can't get stuck on the homework, just come by. I'll be glad to help you.